In this fourth part of Lecture 11 of ELEC5300, I'd like to just close with two applications of the Carhoonen-Loewe transformation. The first application will look at the case where we have a white noise or a signal which is added, to which is added white noise. So let's just look at the white noise case first. And the question is, well, what is the definition, what is the Carhoonen-Loewe expansion for white noise? Now, white noise is definitely not periodic, right? Because there's no repetition at all in this. Every sample is drawn kind of independently. And so for white noise with the covariance function, even though it depends, it's a stationary process, right? It depends on the time shift T1, T2. This is not periodic. It's a delta function, and now we're dealing with continuous time white noise. So this delta function is the continuous time delta, which is undefined at the origin and 0 every place else, but it integrates to 1 if you integrate any interval containing the origin. So the Carhoonen-Loewe expansion equation in this case becomes very, very easy, right? Because everything becomes easy in the case of white noise. Right. And so the reason is that, well, now when I substitute the Carhoonen-Loewe integral equation, the covariance matrix here becomes a delta function. And so when I have a delta function inside here, this integral actually, which normally would be really difficult to handle, becomes very easy, right? So when I integrate this thing from 0 up to t, I just get the value here where t2 is equal to t1. Right? So I just get phi at time t1. Times sigma squared, the variance. And if I look at these two things here, right, this equation basically says, well, lambda n, right, for all n, lambda n should be sigma squared. Right? So all the lambdas are the same, all the variances are the same. In other words, it's kind of flat, right? Remember, white noise has a flat power spectral density. But this one here really says, well, then the basis functions actually can be arbitrary. It doesn't really matter what you choose. So you can choose, for example, the Fourier basis function. That's totally fine choice, in which case you'll have an interpretation of these lambdas as being the power spectral density of that process, right? But you can choose them to be whatever you want, anything that you want, just because this is kind of satisfied for any phi sub n, right? If you choose lambda n equal to sigma squared. Okay, so that's nice, because what it says is that white noise really is very easy to deal with, because you can use any kind of orthonormal set of basis functions to expand it out. So you can look at the case, well, suppose we have a random process plus white noise. Why is this so easy to deal with? The reason that it's so easy to deal with is that even though this process x of t here can be very, very complicated or have some kind of complex basis functions that you need to expand it with, because the white noise is so flexible, it has any kind of basis functions are fine with it. You can just, if you know some basis functions that you want to use for the xt here, you can just use it to expand the wt. And so that means that this process here, y of t, can be expanded with a Carhoonen-Loewe transformation, which is exactly the same Carhoonen-Loewe transformation as x of t. The only difference, of course, should be that the components or the coefficients should have larger variance, right? Because now instead of just having the having to describe x of t, it has to describe x of t and w of t. So let's assume that then therefore that x of t already has some known Carhoonen-Loewe transformation. I don't know how I found this, but somehow I found this Carhoonen-Loewe transformation. So I found those basis functions phi sub n, and I'm going to put a little x here in the superscript here to indicate that these are the ones that I found for x, right? And if I'm just trying to expand x, I have these coefficients, right? And the coefficients all have variance lambda sub n, where the x here means that I'm just expanding x alone. Now let's take a look at the the Carhoonan-Loew expansion for y. Right? So now y is x plus w, and I want to find the Carhoonan-Loew expansion for that. So this is just the standard equation that I had before, and I'm just going to place here phi sub n with phi sub n of y to indicate this is the Carhoonan-Loew expansion for y, and it has some coefficients here, lambda, which also depend on y. I'm going to substitute in the covariance function for y, right, which is just going to be, because x and w here I'm going to assume are independent, is just going to be the covariance function for x plus the covariance function for w. Right? So because w is white noise, its covariance function is a delta function, and this is just the covariance function for x. So I've substituted this with that. Right? And then I can just expand this out, so I can take the integral of this times this and add it to the integral of this times this. And when I integrate this times this, I get exactly the same result, where I just get it equal to when t2 is equal to t1. So I just get a t1 here, and the integral disappears. I've evaluated that integral here. And this. Right? So now I can take this one here and say, hey, that looks exactly like this, so I'm going to take this and move it over to the other side. So I'm going to take this, and then I'm just going to get a lambda minus sigma squared down here times the phi sub n. Okay. So now I'm going to take this thing here, right, and move it to the next page here. So this is the previous page, equations. And then I'm going to say, well, hey, look, this is just the covariance matrix, covariance function of x, right? And so I know that x has a Carhoonan-Loew transformation, which is given by this, right? I've assumed that I've already found these phi sub n's of x, that those are known, right? I don't know what these are, but I know they satisfy this equation. If I say, well, look at this equation, look at this equation here, these are the same, these are the same. So, hey, I should just be able to use the exact same things that I found for x for y. Right? So the Carhoonan-Loew basis functions are unchanged, exactly because if I find something for x, then the because I added white noise is totally fine with whatever basis functions you use. You can just reuse the ones that you use for x. So that's what we said before, and we find it, it falls out of the math. And then in order for this to be true, the only thing I have to do is match this term here with this term here. And so that just says, well, the lambdas for y are just sigma squared times bigger than the lambdas for x. Right? That's equation here, because the lambdas for y have to account for not only variation in x, but also variation in the white noise. Okay, so that was another example of why we like to deal with processes that are white, because they're somehow more flexible. We have this now new notion that somehow white noise kind of can look or can be expanded in terms of any set of basis functions. I'd like to close this section then by talking about a final example where the covariance function has a really kind of complicated looking form where you think, well, maybe this thing should fail because I don't know how to integrate these kinds of functions. But in fact, it actually all works out. So the process I'd like to look at is the Wiener process here. And so if you go back and you look at our discussion of the Wiener process earlier, you'll see that, well, it has this covariance function Cx t1 comma t2, which is the minimum of t1 comma t2. And the intuition I told you there when I presented this was that, well, the covariance function is just a relationship between the Wiener process at time t1 and the Wiener process at time t2. But remember, the Wiener process is just the integral of white noise, right? So the process at time t1 is just the integral of white noise all the way up to time t1. The process at time t2 is just the integral of white noise all the way up to time t2. So if you think about, let's say, a time axis here, this is t. If the Wiener process at time t1 is just the integral of some kind of white noise process all the way up to time t1, the Wiener process at time t2 is just the integral of that same process all the way up to time t2. And so they have this kind of shared history all the way up to time t1, if t1 is the minimum. Right? And then between T1 and T2, the Wiener process time T2 is seeing something different. It's integrating something different. But whatever's here, because this process is white, is totally unrelated to what's happening here. Right? So the covariance, right, the kind of the relationship between the value here and the value here only depends on this common history, right, which is the Wiener process up to time T1. If T1 is less than T2, and of course if T2 is less than T1, we choose T2. So whatever one is smaller determines the covariance, right? And if this if I was integrating white noise with some covariance sigma squared, then I would just have a sigma squared over here. But so I'm assuming that here the process that I'm integrating, the white noise process, has variance 1. So now you can say, well, look at this kind of complicated looking covariance function. Suppose I just simply stick it into the Carhoonen-Luebbach integral equation. I got this min of t1 comma t2, phi k t2 dt2, and I look at this, I say, this looks pretty difficult to evaluate. Right? But in fact, it's not that bad. Right? So what we can do is we can say, well, I am going to integrate this thing all the way up to from t2 from 0 up to time t. Right? So t2 is the thing that's varying, right? And t1 is actually fixed. Right? This has to be true for all t1s, but when I'm doing this integral, t1 is fixed. So if t1 is fixed, right, and I integrate from 0 up to t2, then I have two things I have to do. First, I have to integrate this thing all the way up to t1, right? So when I'm integrating all the way up to t1, then the minimum, right, is just t2, right? So this minimum is t2 times phi sub k. This is the same thing, dt2, right? And then I integrate for t2 from t1 up to big T, right? But now, since I'm integrating from t1, T2 is bigger than T1, so the minimum is just T1. Right? So this is the minimum here, and I get this thing here. Okay, so at least I've gotten rid of this minimum thing. Right? That is good. Right? This still looks a little bit difficult to deal with because, you know, I've got a T1 here, right? But I've also got a T1 in the limits here. So now I'm just not just multiplying by T1. I got a T1 in the limits here, and I got a T1 inside the function here. So this kind of looks like it's going to be really hard to deal with. So I'm going to do this little trick where I kind of try to get rid of the T1s by differentiating. So I'm going to differentiate this thing with respect to T1. And so when I do that, I differentiate this thing, this integral here, nothing inside here depends on T1. So when I integrate this integral, when I differentiate this integral, which goes up to T1 with respect to T1, then the opposite of integration is just differentiation. So I'm just going to evaluate, differentiation is just going to get rid of this integral here and replace this by T1. So when I differentiate this with respect to T1, I get this term here. When I differentiate this thing here with respect to T1, right, then I have the product rule because I have something here that depends on T1 multiplied by something here that depends on T1. Right? So the product rule, if you remember, if I let's say dx of a times b, right, that's just a prime b plus b prime a, right? So first I differentiate the first term with respect to x multiplied by b, and then we'll differentiate the second term with respect to x multiplied by a, right? So here, if my two terms are, you know, this one here and this one here, right, then when I differentiate with respect to the first term, this one here, I'm just going to get 1, and I multiply by the second term, so I just get this integral here. And when I differentiate this thing here with respect to T1, instead of getting the integrand here evaluated at t1, I get minus the integrand because it's at the bottom here. So I get minus this thing evaluated at t1 times a, which is this t1 here. So I get minus t1 times phi k t1. So I've gotten rid of at least one of those integrals, this one here, right? Now, the other thing you can see that's nice is that this thing here and this thing here are exactly the same, right? So I can cancel this, and I'm just left with this single integral right here, equals to that. So let's take this up here. This is exactly the same equation that we got from the previous page. And what I'm going to do is I'm going to differentiate this again because I've still got the t1 here. So I want to get rid of this t1. So I want to differentiate this with respect to t1. It's in the limit, so I just put the t1 inside here. It's in the bottom limit, so I put a minus sign here. And I have to double differentiate this thing again with respect to t1. I mean, differentiate this thing again, so I got the double derivative with respect to t1. And so now what I get is, well, here I get a function whose double derivative, right, is proportional to the negative, right? And that's a sine and a cosine, right? Because if I take a, let's say cosine, right, I differentiate cosine, you know that you get minus sine, right? And then when you differentiate the sine, you get cosine, right? Back again, right? So if you differentiate cosine twice, you get minus cosine, right? If you differentiate sine twice, you get minus sine, right? And each time you differentiate the sine or the cosine, you have to, by chain rule, multiply by the frequency, right? The lambda sub k, right? So the lambda sub k is somehow related to the frequency, or more particularly the frequency squared. And so now you can see that this thing has these kinds of equations here, where the lambda sub k appears here with the square root because I've double differentiated, which indicates the frequency should appear twice. So lambda k here is actually 1 over the frequency here, because when I double differentiate, the frequency will appear kind of over here, right? So this will have to cancel that out. So now I know that phi sub k is some kind of sine or cosine, and in fact, if I just take it, say, well, a sine and a cosine, and I add them together, I'll get another cosine with some kind of random phase shift. Right? So the a and the b here, I can control them separately to control the magnitude and the phase of the final sine wave or cosine wave, which has frequency which is 1 over this. And so now I have then found out the functional form of the basis function, right? So these are the basis functions that I have, right? It's a whole function, which means it looks like it would be really hard to figure out what the function is, right? But now I know what the form of the function is, and the form of the function here really only depends on the a, the b, and the lambdas. So for each k, then, I just have to figure out, well, what is the corresponding a, b, and lambda sub k. And so how do I find that? I'm just going to take this equation here, and I'm just going to substitute it back into the original equation. I know what the phi looks like. I just need to figure out these parameters. And to figure out the actual parameters, I'm going to consider the behavior at the boundaries of the integral on the left at 0 and on the right at time t. Right, so let's just do that. This equation here on the top is just the integral equation that we saw before, where we substituted in the exact form for the covariance matrix, right? So this is really from taking the covariance function here, substituting them in, and then expanding this thing out like this. So this is here, and now I'm just going to substitute the exact form that I found for the phi's into that equation here. Right. So this is still looks kind of difficult here, right? If I substitute in sine and cosine into here, but now I'm going to use the fact that, well, I only need to know this thing at some discrete points because I just need to find these three variables here, a, b, and lambda. So I'm just going to look at the 2 points of t1, which is the most convenient for me. The first one of those is when t1 is equal to 0. And the reason that that's nice is because, well, if I substitute t1 equal to 0 here, then I get an integral from 0 to 0, which is just 0, so that disappears. I get a plus t1 times this, but t1 is 0, so this disappears. Right? So the whole left-hand side of this thing is equal to 0. Right? And then when I substitute t1 is equal to 0 inside here, I just get lambda k times phi sub k times 0. And now I substitute in phi sub k. Now I substitute in the exact form for the phi, which is just a sine plus b cosine, right? Evaluated at 0, right? This whole thing has to be equal to 0, right? But now cosine of 0 is equal to 1, right? So if this whole thing has to be 0, right, then the b here has to be equal to 0, right? Because like when I substitute in 0 here, I get sine. So I can't do anything to when I substitute in 0 here, sine of 0 is 0, right? So that will knock this whole thing out, right? So a doesn't enter into this equation at all. Let's just knock out all the stuff that doesn't. This is 0. So the only thing that's left over here is b times 1 is equal to 0, and that means that b must be equal to 0. Okay, so b is equal to 0, and so therefore actually this equation that I got here is equal to 0 becomes even simpler. It's just a times sine lambda sub k. Right, so now I know that. Now I'm going to substitute t1 is equal to t into this equation here. When I do that, when t1 is equal to t, I get an integral from t to t, which is 0, so this whole thing will knock out. Right? Then I put the t1 inside here, so I get that I get an integral. Oh, sorry. Okay, I'm not going to use this equation here. I'm going to use this equation here. Right. Sorry. Integrate. So this equation here was what I got from differentiating that thing once. Right, so this differentiating this equation here once. So I'm going to substitute that equation. I'm going to substitute t1 into here, but again. Just like I said, when I substitute t1 is equal to t here, this integral here disappears, right? Because I'm integrating over something with length, an interval of length 0, and so I get this times the derivative of the basis function is equal to 0. Then what I get is this equation here. Where I have to differentiate this thing once, right? But I already know that phi sub k is equal to a times sine of t divided by square root of lambda sub k. Sorry, this should be a k here. Let's just correct that. It should be k. And so when I take this and differentiate this, right, I'm going to get a sine to a cosine, right? So I get a times the cosine of this thing here, where I've substituted t1 is equal to big T here. So cosine of t divided by square root of lambda sub k, right? And then when I differentiate this by chain rule, I have to take out one of the square root of lambda sub k's to the outside, right? So that's just chain rule to give me this. Right? And this thing has to be equal to 0. So I can't choose a is equal to 0 to make this true, because that would be stupid, because if I chose a equal to 0, then a and b are both 0, I just get 0, right? It doesn't have norm 1. So I can't choose a is equal to 0 here. So the only way to make this thing 0, I have to find the lambdas here, so I can't choose these, right, is to... Oh, sorry, I have to find these ones, so I can't set these ones equal to 0 because that would give me only kind of one value here. So what I'm going to do is I'm going to look at this part of the thing and set this equal to 0. Right? So the cosine, where does it equal to 0? Right? Well, the cosine function remember, looks something like this. Right? It starts out at the origin, kind of comes down, and comes back up. Does the same thing over here, and actually it's 0 at an infinite number of points here, where this first point here, where it goes to 0, is pi divided by 2. Right? And then at this point here, it goes up. This difference from here to here is pi. Right? So it first goes to 0 pi over 2, and then the next point is pi over 2 plus pi, which is 3 pi over 2, 5 pi over 2, and so on. So I can express that compactly as k, where k can be any integer here, minus 1/2 times pi. So when k is equal to 1, I get pi over 2. When k is equal to 2, I get 2 minus 1/2, or 3 pi over 2, right? And then so on. K is equal to 3, I just add another pi here, right? So just each time I increment k, I'm just adding another pi here to this equation. Okay. And so now I can just solve this thing for lambda sub k, right, by moving the lambda over to this side, dividing by k over 2, and then squaring everything. And so I get this expression for lambda sub k. Right? So now because the cosine here is equal to 0, at an infinite number of points, I can get an infinite number of lambda sub k's, right? And the lambda sub k's are going to be decreasing with k. So the first lambda sub k is going to be the biggest one. That's going to be the coefficient with the largest variance, and then it's going to kind of start decreasing as 1 over k squared, something like that. So in order for the final thing we have to do then is we found the lambda sub k, so we found the lambda sub k's, right? And the b's we know are 0 from this. And so the final thing we have to do is find the a's, right? And the a is just kind of scaling the magnitude of this basis function. So we just have to choose the a so that this basis function has unit norm. So I just have to integrate the basis function squared from 0 to t. And when I do that, I get a squared times something, where this is integral, I can evaluate it. And if you evaluate it however you want to evaluate it, you'll get t divided by 2, and you just have to set this equal to 1. Right? So when you set that equal to 1, then a should be the square root of 2 divided by t. Right? And so then summarizing, then the basis functions have this form. Right? It's phi sub k is equal to a, which is this, times sine of t divided by square root of lambda, where square root of lambda is the square root of this thing here. And when I divide, I get this on the top and this on the bottom. Okay, so that's the form of the basis functions. And now let's take a look at what these basis functions actually look like for different values of k. That's what's shown on the top here. So the first one, k is equal to 1, which you remember had the largest covariance, the largest variance, or lambda sub k. So when k is equal to 1, I get the largest variance. The most important component is going to be the one that is this sine wave here, right? When k is equal to 1, I get, suppose t is equal to 1, I get 1/2 t, so pi over 2, right, t. And so at the end, when t is equal to 1, I get sine of pi over 2, which is the point where it reaches maximum value here. Right? So it reaches its maximum value over here. And so this is kind of describing the overall trend of the Wiener process, right? So remember, the Wiener process is describing this gradual drift, and it could be gradually drifting overall, to the left or to the right. It's equally likely to go in both directions, but it's going to drift farther and farther away from the origin as time goes on, and that's kind of reflected by this general trend away from the origin, or at least the uncertainty gets larger, so the position will be somewhere far from the origin, probably, right? And then the other basis functions, k is equal to 2, would be this red one, are just going to be higher, this k is equal to 2 is this green one, are just going to be higher and higher frequency components, right, which are going to add more and more detail to the thing. So if I take this Wiener process and I kind of like look at, imagine what it's going to look like. it's going to start out here at the origin, and then it's going to start, bobbing around, and then maybe it's going to go up here, and then come down here, and stay here for a while, and go up and then go down, and whatever it's going to do. I don't know, what it's going to look like, but it's going to have some kind of strange shape like this. So it has frequency content at all different kinds of value at all values, right? So it's going to be described by an infinite number of basis functions with higher and higher frequency, but they're going to be less and less kind of important. So the coefficient variance kind of going down is this 1 over k squared that you see here. But the basis functions capture the main properties of the Wiener process. Number one, all the basis functions start out at 0, right? That's because I know that the Wiener process starts out at 0 and then just starts drifting from that point. That's always the assumption, right? And the other thing that you're going to notice here is that, well, here all the basis functions at the final point here have 0 slope, right? They're always peaking here at the maximum or minimum of the sine wave. So they have 0 slope, and that's kind of indicating that, beyond this point, you don't know whether the process is going to go up or going to go down, right? So even if it's kind of trending up at this point, it really doesn't mean anything about what's going to happen after that, because it's integrating white noise, right? So going beyond this point, if you were going to predict what it was going to be, you should just predict what the last value was. Right? And that's kind of indicated by the fact that these guys are all flat at the top. So you can see that this set of basis functions is not quite the same as what we got for periodic basis functions, but it's somehow capturing the specific properties of the Wiener process. In particular, we pointed out the initial value being 0 and the fact that after this point you can't predict anything, so your slope should be 0 at the end here. Okay, so that's 2 examples of the Carhoon-Loewe transformation and how it can kind of be useful in expanding out processes in terms of different components which are not necessarily sinusoidal like we used in the power spectral density analysis or the Fourier analysis.